Hey there, I'm Andy Parker, so you can't quite see the top of my head. I'm the president of Lucid Equipment, and behind me is James Guerrero. He's a field engineer for Zeiss, and we are here putting together this LSM 700. Yeah, Zeiss LSM 700 confocal microscope, and the purpose of this video is to show you that it works. Probably zoom in and out here as we go.
Sure. So there's no camera, but you can look through the eyepieces and see that there's a sample. You know, you can see the sample.
Actually don't.
Oh, that's because I switched off. Now you do. Yeah, now you do.
Oh wow, cool.
Yeah. And then you can change different color, right?
Green to red.
Yep.
Yep.
Yep. Blue.
Kind of lost it.
It's probably just the sample is not good for.
Lend a little heat to it.
Yeah, it's just the lamp intensity. Yeah, it's in there.
There we go. That's really interesting. What is that?
Convoluted.
Convoluted.
Yeah. That's all I ever look at. Okay, so then here I can go over to the laser scanning part of the system.
Yep.
And do a smart setup. So this is just typically how any user would set it up, or the most basic, but so all three channels, just to show that all three detectors are gonna take an image. You know, you could do this on one channel, but just capturing the whole thing at once. Like if all this works, that means that it's all, you know, that all three internal detector channels work.
Okay. That's perfect. We can see right over your shoulder too. Just gonna zoom in here on the screen, maybe, if I can. There we go.
So that's three channels right there.
So red, blue, and green.
Yep. And I can.
All right. So you can still see red,
Yep.
blue, and green right in
And
there.
you can actually go here. So this is a split screen.
All right.
This is each channel individually, and then the combination.
Sweet.
So we can do that and just make it look nice. You know, close the pinhole down. Let's do this one more time.
Interesting.
And this is just doing like what a user might do automatically, just setting the exposure correctly and everything. It's just one more I did with the pinhole closed so that it's, you know, make sure the pinhole closes right and the acquisition is as good as it can be. So it looks good. That's how I would expect it to. Then the other function is a Z-stack, and this just moves the focus drive up and down, so it gets a little
tighter.
Yeah. I mean, it's just going to go through the depth, so it's going to take a couple different images at the top and the bottom, so then you could like zoom through the whole sample.
Got it.
Think of this real quick. This is faster.
Fascinating.
Yeah, it's pretty cool. So Z-stack.
What level can you get down to here? Like you can't quite get to the atomic level, obviously.
No, I mean, I think I don't know the nanometers that these can separate that the 700 can. I mean, I can find out for you. I can look it up.
Hey, it's not that.
Yeah.
Or just my curiosity.
This is going to take a minute because this is now a much more complicated experiment.
Yep.
But so now it's doing an experiment instead of just doing one scan. Yeah, it's starting right here, and it's going to take multiple images, and it's going to move up one slice.
I see. So it's literally
It's taking an image and then it moves up a little bit, takes another one, and
Yeah.
another one, another one, another one, and then it puts them all together, and then it has a stack. So it's taking an image at different focal planes.
Right. So I mean that's got to be a nanometer or 2 nanometers. I mean this is incredibly thin. There's
Yep. Yeah. Oh, of course. Yeah.
Yeah.
So yeah.
there's
It's
nothing inside.
the intervals are 1 micron.
Yeah.
Yeah.
Okay.
I mean, right now, while we're doing this, I have the heat blasting away. So I don't know if you want to zoom in on this.
Yeah.
I don't know if you can see this, but this insert right here.
Yes.
This is one of the heated inserts. I mean, all you can do is feel it. It's warm. It's warm to the touch.
Yep.
Yep. This is on its way up. You know, it's at 37. It's at 36.9. And then inside the XL heating unit is blowing heat inside, and I mean you can stick your hand in there and feel it.
Yeah.
It's set to 29.5, and it's been going up. Could take an hour to
Couple minutes,
get to the total temperature, but it was started at 18 Celsius and now it's at 26.
Right. And so what somebody would do with that incubator plate, I'm assuming, is that they would take a live sample
Yep.
and then grow something on it.
Yep. And there's a CO2 module, so yeah, you can keep your cells alive while you image them over a long-term, like nighttime, over 24-hour experiments. Sometimes people leave the cells on for the whole time, and they set up a time lapse. So every so often it takes another picture.
Right,
And
I see.
Yeah, and then it just to see if the cells are growing or if they're dying or whatever.
So you take the sample. You take the sample, then you can walk away.
Exactly.
You take the sample, you set the machine up, you run the experiment, you walk away.
Yep.
It runs the experiment for you.
Exactly.
That's really fascinating.
Yeah.
And so you can probably see things
Yeah,
live
yeah.
and die.
You can, yeah.
Yeah.
It's pretty cool. Like I mean, I don't see a lot of it in the job, but I see people and talk to them like they got worms in there and they watch the worm go through like the whole life cycle, born and die in this little tube. It's pretty cool.
Yeah.
Or like cell splitting and stuff like that. It's really interesting.
So they're looking for pathology.
Yeah.
Yeah.
Yeah. So it tells you, see, it says it's 3 minutes, there's 3 minutes and 20 seconds left of a 6.5 minute experiment.
So 3.5 minutes left. There you go.
And after that I can just check see the zoom works. And that's pretty much it. I mean, this is exactly operating how I would expect.
Good. We didn't even set the table.
Didn't float the table, no. I mean, look at it.
Not necessary.
Yeah, you'd see if the table wasn't floating and there were vibrations in the room, you'd see the zigzags.
Fuzzies.
This whole, yeah. I mean, it's so obvious you'd notice right away.
MRIs are like that. Like you actually have to oftentimes build a pad
Yeah,
that the MRI sits on.
yeah. I helped install this transmission electron microscope at Harvard that's like, it's on a like 10-foot by 10-foot block of concrete that are on giant springs, and it's in a temperature controlled room in the basement, because like any vibrations, even any, if the temperature in the room changes by 3 degrees in an hour, that will totally mess up the whole system. The whole system, yeah. It can't work. And when this is when I first started with Zeiss, and when I was there doing it, I was like sitting there while they were doing this, and I had my hand on the table, and I was doing like this. It's all connected, the whole thing is one unit,
Yeah.
and I wasn't doing it on purpose, I was just, distracted, like just doing this. And all of a sudden there's all these lines all over the screen. They're like, they're like looking around. They're like, oh, you can't do that. You can't touch anything. Like, it was just crazy. Like that, such a little thing could. But that was atoms. I mean, we were looking at atoms.
Yeah.
I mean, it doesn't look like anything, just these little dots on the screen. But it was
Organized
awesome. Yeah.
Yeah. I find that stuff incredibly fascinating.
Yeah, it's really cool.
Yeah. The electron cloud and.
Oh, it's awesome. It's
Yeah.
unbelievable. I mean, it's like, it's a microscope, but it's not even seeing. It's like using electricity to see, and it's crazy.
Thinking of I can't remember the name of the experiment, but it's the slit lamp experiment. It's very famous. So it's like somebody, you can't predict exactly where atoms or where electrons are, so what they did is they took like these slits, and they beamed light at the slits, and you would think that the light behind the slit would be exactly the shape of the opening,
Mm-hmm.
but it's not.
Mm.
And it's not, it gets much bigger because electrons are
Bounce around, yeah.
they bounce around.
Yeah.
And it's like this sort of mathematical prediction model.
It's great. Yeah. I mean, that's what the electron microscope does. Like it uses the way the electrons hit in some algorithm that like figures out what they did when they passed through the sample, and that's how they make an image.
Yeah.
It's
Fascinating.
It's not like a camera where it just opens up to the light and the light hits it and then it recreates it. It has to use some algorithm it's just amazing.
It is. Yeah. Really cool.
So it's almost done.
Cool.
55 seconds.
Be patient. We had that 9 Tesla MR here that I was telling you about.
Mm-hmm.
Never got to fire that up though. You can't fire up a 9 Tesla MRI wherever
That's
you want.
crazy, yeah. It's the magnet, right? That's what.
Magnet,
yeah.
yeah.
Wow. That's
Yeah. And that would pull the fillings out of your face.
that's crazy.
Yeah. Really cool.
All right, all done. So then, if I just do this, you can see that's how it went through.
Oh, I see. So
Yeah.
now it's showing us the slices.
Yeah.
Fascinating.
Yeah.
So what are these little spots in the center?
I'm not sure.
I mean, they could
There's some
nuclei.
kind of nuclei. I'm
Yeah.
pretty sure. Yeah. Yeah.
Nuclei of some sort.
Yeah.
All right. Wait, you pronounce this thing working?
I do.
Okay.
Yeah.
Yes, working. All right. Thank you very much. I'm gonna stop this now.